what I'd like to show you is that quantum magnets also sometimes have to cope with frustration. But I'd like to show that while they're coping with it, they actually manage to find various interesting ways to do that, and realizing various novel phases with unique excitations that they can host. Okay, but before I talk about quantum magnets, let me just mention that I'm generally interested in many-body systems. Okay, and many-body systems are systems of many particles that are interacting. In particular, electrons, but those could be also other particles like atoms and traps, etc. And of course, what makes systems of many particles interesting to study is that more is different. Okay, and as Philip Anderson tries to explain in his seminal paper, it's really impossible to understand the behavior of large and complex aggregates of elementary particles just from simple extrapolation of the properties of few particles, right? And instead, at each level of complexity, entirely new properties appears. Okay, so that's the main thing I find exciting about studying many-body systems, and this is even more true in the quantum regime. Okay, when we go to low temperatures and quantum effects start to affect the behavior of the particles. Okay, so I'll focus now on magnetic systems, and when I talk about magnetic systems, I actually mean systems of localized spins or systems of localized magnetic moments. So those are systems in which the electrons are immobile, for example, and in practice, if I'm thinking of like actual electronic materials, the electrons can be pinned to the lattice, and sometimes it just happens due to very strong repulsions between the electrons. Okay, which are called Mott insulators. Okay, so this will be systems that are electronic insulators, and only the spin degree of freedom of the electrons can now fluctuate or interact. So this kind of systems, we run into this kind of basically every day, and we know that when we cool them down, they often tend to order. Okay, so for example, in iron, when we cool it down, will become a ferromagnet where all of its spins are pointing in the same directions, and then various oxide materials will become antiferromagnetic, so the spins will kind of point in opposite directions, but there will still be an ordering pattern in the material. Okay, and this kind of system we understand very well. In particular, their excitations are easy to understand. These are just spin waves, or in their quantized regime, single spin flames, which are magnons. Okay, so I could take a ferromagnet and flip one of the spins. This spin can now propagate, and I can think of this spin essentially as a particle, right? And an important point is that the single spin flip is a spin 1 excitation, right? It's flip the spin of -1/2 to spin 1/2. Okay, and we know kind of the dispersions these things can have both in a ferromagnet or an antiferromagnet. But today I'd like to ask, is there some alternative to order in the systems? Can a clean magnetic systems, okay, so without introducing any intrinsic disorder due to impurities, etc., can we suppress order due to just purely quantum effects, okay, quantum fluctuations at 0 temperatures? And I'd like to argue that, at least in theory, okay, we can. And such phases that are not ordered due to quantum fluctuations are called Spinliquids. Okay? And of course, what's interesting about them is not that they're not ordered, but that they, when they're trying to avoid order due to quantum fluctuations, they have to find the way to do this. Okay? And when they do it, they typically give rise to new phases of matter, which host new excitations or quasi-particles. Okay? So generically, when we think of spin-liquid states, they can be divided into 2 categories. One are gapped spin liquids, So when there is some gap above the ground state, and then the excitations that we have are topological excitations. Okay, so these are similar to the excitations in fractional quantum Hall states. But there we can also have gapless Spinliquids, and these are states that essentially behave in which the spins behave have some kind of metallic, give rise to some metallic behavior. Okay, so these are insulators when you're measuring electric transport, but when you'll be measuring, for example, thermal transport, they'll essentially behave like metals. Okay, and maybe to very briefly give you an example of how such quasi-particles or orders could arise. Let me demonstrate this in a very simple model. Okay, so typically what we need to make the system avoid ordering is some kind of frustration or frustrated interactions. Okay, so one such option is having anti-ferromagnetic coupling. Okay, so it's a coupling when spins want to point in opposite directions. And now the question of what would be the ground state or the state of the system when we cool it to low temperatures depends a lot on the geometry of the system. Okay, so for example, when our system is, when we think of a system of spins on a square lattice or a cubic lattice, we can order the spins in a way that everyone will be happy just by forming this L ordered state. Okay, but once you think of spins on a triangle lattice, for example, right, you can see that if two spins are anti-parallel, then the third spin is already frustrated. It doesn't know what to do. It wouldn't know who to anti-align with, right? Okay, and so we can ask, okay, what could spins in the quantum regime do if they cannot order? Okay, and to understand that, we could think of starting from just a pair of spins. And we know that the pair of spins that are anti-ferromagnetically coupled wants to form a singlet state. Okay, so it's a superposition of up, down, and down, up on the two sides, right? Now, this could suggest that on a lattice, for example, we could try and pair every pair of neighboring spins into such singlets. Okay, so here this is a triangle lattice, and each blue solid line indicates that we paired spins on these two sides into a singlet. Okay? So those could potentially be a candidate for a ground state. Of course, an equally good candidate would be a different arrangements of spins into the singlets. Okay, or this one, etc. And kind of this way of thinking was proposed by Anderson back in '73, suggesting this novel state of matter, which is the resonating valence bond. Okay, in which the true ground state of the system would be a superposition of all these different coverings. Okay, and you can see that this state would indeed not have any kind of long-range magnetic order. It would have strong quantum fluctuations. It would be fluctuating between a macroscopic number of states, essentially. Okay, but what is interesting is that we could think of excitations in these systems, right? So to create an excitation in such a state, we basically need to break a single bond. Okay, and when we break this bond, for example, we're basically creating a spin 1 excitation by making the singlet state into a triplet with 2 spin ups.
So this is gapped.
This is gapped, yes. And now what's interesting is that this, we basically created the spin 1 excitation by creating 2 spin 1/2 excitations, right? And now these 2 spin 1/2 excitations can propagate freely. Okay, so we managed to fractionalize our spin 1 excitations, which was the basic excitation when we were talking about ordered systems, into 2 spin 1/2 excitations, which are often called spin-ons, which are fractionalized excitations. Okay. Now it's also possible to show that this state has topological features. Okay, these excitations are topological in their nature when we consider another set of excitations. Their statistics is not trivial, but I won't go too much into that. Okay. Of course, an interesting question now to ask. I gave you some theoretical proposal, but eventually we're physicists, or we want to understand whether this kind of states can be realized in real materials, where this kind of quasi-particles can actually exist. And there has been, over the last few decades, a lot of proposals for various materials where various spin-liquid states can arise. So I'll just flash a few, like the Herbert-Smithite, where it's actually a lattice of a Kegelman lattice that the spins live on. Okay, so it turns out that the simple triangular lattice is not frustrated enough. Okay, but on Kegelman lattices, we believe that this kind of states can appear. There are various organic materials which are kind of triangular, but they also have further neighbor interactions, which give further frustration. Recently, there is a lot of excitement about a novel material which is called ruthenium trichloride, where the frustration comes due to anisotropy interactions. But unfortunately, there are still no kind of very clear indications of spin-liquid phases. Okay? So this, of course, kind of calls for trying to think of both novel probes, of course, of how to probe spin-liquid behavior or this kind of excitations, but also novel kind of platforms or routes towards where this kind of states could arise. And one such platform that people are thinking about is this new regime of van der Waals Moiré systems, okay, where you could, so it's a whole new field, kind of got exploded once with the observation of twisted bilayer graphenes, where if you take two graphene sheets and twist them by a small angle, you can form Moiré patterns that are triangular, so you already think that there would be some kind of frustration. And what people observed is that there are indeed kind of a lot of interesting phenomena which are related to the strong interactions between the electrons in the systems. And so I mentioned twisted bilayer graphene, but of course there are a lot of other van der Waals materials where Moiré patterns can arise, and people saw interesting things happening. But essentially, once we have some kind of correlated insulating states, so states that are becoming insulating due to the strong repulsion between electrons in the system, you could also ask whether, whether this insulating states, when you think of this effective spin of the electrons, what kind of phases would they realize? Would they be ordered or not? And what kind of helps here to enhance frustration, okay, or enhance quantum fluctuations, is the fact that there is additional Valley degree of freedom, okay, which potentially could make the realization of quantum spin liquids more likely or more easy to find in this kind of systems. Okay. So without going into too many more details, I wanted to just tell you that the search for this new phases of matter, which are the quantum spin liquids, is first of all fun, both on the theory side and the experimental one, and it's still ongoing, both in the search of searching for novel platforms and novel probes to probe this kind of behavior. But maybe the main take-home message is that frustration is not always bad. It kind of forces you to be also more creative. Okay. Thank you.